Hi everybody, welcome back. In this next sequence of videos, we're going to be looking at a little bit at some of the underlying characteristics of ordinary least squares estimation for regression analysis. So OLS, or ordinary least squares, this is just one way that we could use to estimate some relationship. So ordinary least squares right? And this is what we've kind of talked about in previous videos, where if you had only two variables, an x and a y, and you have some data here, some data points, ordinary least squares is finding that best fit linear regression line that's going to minimize the sum of squared residuals. And so the residuals are here, we square those, we find the best line that's going to minimize the sum of all those residuals, and then we have our y is equal to beta 0 plus beta 1 x. Okay, and because we're mostly emphasizing causal econometrics here, we're interested in getting the best estimate for beta 1, which is the relationship between x and y. So a 1 unit increase in x is associated with a beta 1 unit increase in y. Okay, there are other ways you could estimate this. You could, instead of using the beta 1 estimator, which if you recall is the covariance of x and y over the variance of x, you could just use the average of the data. You add all those up, take the average, and that could be an estimator. You could use other different estimators. There are other ones that you can use in more advanced econometrics. But OLS is nice because OLS is what we call blue. Blue, which stands for B for best linear unbiased estimator. Okay, and each of these have an actual meaning behind them. Best stands for minimum variance. So it's an estimator that's going to not have a huge variance, but a small one. We'll talk about that in a second. Linear, which is linear in coefficients, right? It's possible. So all of these here, this is a linear equation. We could also have something like plus beta 2x squared, and that would be fine because even though the variable is squared, the coefficient is still a linear variable. Yeah, and so it's linear in the coefficients. It's unbiased. So what we're meaning there is that, the expected value of the coefficients is equal to the true underlying value. So if the true beta is, say, 5%, then the expected value of beta, especially as the sample size increases, is going to get closer and closer to that 5%, that true variable, that true value. And this unbiasedness is something that's super important, because if we think somebody has if some relationship has a 1-to-1 relationship, but it has a 2-to-1 relationship, then the policy implications or the business implications are going to be very different from each other. So, and then the last thing is that it is the estimator, which means it's estimated. It's not the true value. Okay, and a couple more things related to this. As the variance or as the number of observations increases, the variance decreases. Okay, and if we want to see what that looks like visually, then if we had some distribution with, say, 5 variables or 5 observations, and we have an unbiased estimator here, that's fine. But as we increase our number of observations, we're going to get a more and more precise estimate of the data, so of the relationship. So that variance is really going to get smaller as we ramp up that sample size, and we're gonna hone in even closer on that true effect. The unbiasedness is very important because if we have, for example, let's take the same n equals 5, and this is our beta hat. Well, if the true beta is over here and we increase our sample size, then we're just more precisely wrong. And so if we have unbiased estimates, if we have biased estimates, that's going to be a huge problem, especially as the sample size increases. And with data in today's world, we typically do have very large sample sizes. So it's very important to make sure that we focus on an unbiased estimator. So OLS is good for that. But there are going to be some assumptions and some properties here that we're going to talk about that are going to have some critical implications on which problems we try our best to address. All right, because you're gonna always have some potential problems with heteroskedasticity, multicollinearity, things like this. We're going to talk about those. But some problems, they are associated with a difference in the variance, but they don't affect biasness. But some problems, they affect biasness, and those we really want to be thinking about. So let's dive into some of the properties here of our OLS estimator, and these are called the classical OLS assumptions. Okay, so one, we're going to be assuming that there's normality in the error term. So the error term is normally distributed with a mean of 0. Okay, and all this is doing is that anything that we're not modeling, it can be left up to chance, and we're assuming that all of that randomness left over that we're not including directly in our model, that can be assumed normal. Okay, number 2, we have what's called no autocorrelation. This is also somewhat related to one called no serial correlation. And what both of these mean are that observations of the error term are not correlated with each other. Are not correlated with each other. Okay, a common example here that where this becomes violated is time series data, right? Because if you have a time series, and suppose that you're looking at maybe stock prices over time, well, here's today's stock price, here's tomorrow's stock price, and let's say the next day there's some news and it's going to increase the stock price. Well, that news was kind of random. That could maybe be thought of as happening in the error term, something that we wouldn't have modeled. But now, because of that randomness, well, the next day, the next stock price is going to be associated with that, and maybe over time it might come back, and that randomness might disappear, and we'll get back on the same kind of trend we were on. But in a time series, what happens today is correlated with what happens tomorrow and the next day. And so whenever there's a shock to the system, like for example, COVID, right? We're moving up and then COVID hits. Well, now every day after that, it's going to be correlated with the day before, and we'll slowly work back through a recovery. But time series observations are correlated between each other because what happens today is correlated with what happens yesterday and tomorrow. Another common example, so that's the autocorrelation bit. Serial correlation is the same thing, but you might find this in more kind of cross-sectional data. Common example there might be another violation with neighboring home values. Okay, and so you'll commonly see a correlation between the value of my house and the value of my neighbor's house and the value of their neighbor's house. And so, for example, if my house burns down and now all of a sudden it's just some charred wreckage and it looks awful, and I don't do anything to clean it up, well, so that's gone up in flames. That's now going to affect the value of my neighbor's house because now they're living right next to a pile of charred, house. And so their home price is going to go down, and their home price is going to go down by just a little bit more, and then that's going to kind of decline, and the next block over, those homes, they might go down a little bit, but they're not going to be too much correlated with my house. But neighboring houses, if there's some random shock to the system that happens through that error term, that randomness will be correlated with the value in the next house and the next house and the next house and the next house, and so on and so forth. So it happens in time series. Home values is another common one. Autocorrelation. There are specific ways that we deal with this in econometrics. A lot of basic cross-sectional data, the data that we're going to be working with most for now, you don't really have to deal with this problem too much. And by the way, all of these problems, they have different tests that you can run to check whether or not they're violated. All right, we're also going to assume that there's no heteroskedasticity. I believe I spelled that right. It's heteroskedasticity, yeah. And basically, the other way that we could say the assumption is we're assuming no heteroskedasticity, or we're assuming homoskedasticity. And what this means is that the error term has a constant variance. Okay, I'll give you an example of when this is violated. So, for example, let's look at on this axis, let's use income. And on this axis, let's use savings, or let's do consumption. Consumption as a percent of income. Okay, same thing. We could also have age over here. We'd have a similar effect because age is correlated with income. But so let's say down here at very low levels of income, people, they have to buy a whole bunch of necessities, and so and this is 100% up here. Let's say, okay, well, taxes, whatever. Let's ignore. Let's simplify things. But let's say people spend about 2/3 of their income on consumption, and then they have a third left for taxes and savings. But there are going to be some people who I don't like this. Let's do consumption in dollars, and let's do age here, just because I think that'll be easier. So 20, 30, 40, 50, 60, 70, 80. When someone's younger, they're not going to have as high incomes, and so there are going to be some people who spend, let's say, 20,000, 30, 40, right, thousand per year. There are going to be some people who spend a lot of money, but at lower levels of at younger ages, people are going to be spending less money. Generally speaking, as people get older, they're going to be spending more money. They have kids, they buy a house, right? But the thing is, there are still going to be some frugal 40-year-olds and 50-year-olds who don't buy much, and then maybe at 60, 70, people start reducing their consumption again. But ignoring that part for now, the whole point of heteroskedasticity is when we have heteroskedasticity at lower levels of one variable, the variance is rather small. It's really tight. Like most people in here, they have a lot of people spending just smaller amounts of money. So the variance is very tight. But then you come up here at 60, and now all of a sudden the variance is very large. And ultimately, the way that you can kind of visually see heteroskedasticity is that the variance fans out. And it's different either across age, across time, across whatever this variable is. And in this case, not only does it fan out, but consumption probably decreases as you get older. And so then it fans back in again, so you have even more heteroskedasticity. So basically, if you have a tight relationship and it's constant variance all the time, then your assumption is met. No heteroskedasticity. But if something happens and your data looks like this, you're fanning out, you've got heteroskedasticity. Okay, that's the next one. Let's move on to number 4. And we just have 5 of these, and I won't have as much detail on the next ones. So 4, we have no perfect multicollinearity. This is when no explanatory variable, this is what we're assuming, no explanatory variable is a perfect linear combination of any other explanatory variables. Not perfect multicollinearity, but multicollinearity itself is a fairly common, I guess, issue or problem that or occurrence, I guess, occurrence in regression equations. But in practice, to deal with multicollinearity, it usually involves removing one of the variables. And so let me just give you another quick example here. Perfect multicollinearity could be something like if we want to model wage, and that's going to be, if we want to add some variables here, if we add education, or let's do age, beta 1 age plus beta 2 education plus beta 3 work experience, then this might not be a perfect multicollinearity, but if you think about these three variables, well, your age is going to be very, very related to your years of education plus your years of experience. And so if you can take two variables and you add them up and you're going to get that third variable, that is perfect multicollinearity. And that's that. If it is perfect multicollinearity, that's going to be a problem, right? And so in this case, you would probably only use 2 out of 3 of these variables. And in that case, that would be fine. We'll talk in the next video some more about multicollinearity. Most of the time, removing a variable that you believe should be included in the model is a bad idea. You don't want to remove variables if you think they should be there, because number 5 is the last assumption, and this is the one that is probably the most important when conducting causal econometrics, and that is no endogeneity. And what we have here are a couple different things, and I'll have a whole video talking about this. But we have no omitted variables, or simultaneous equations. And underlying all of this, the idea is that all explanatory variables the x variables are uncorrelated. Let's do that. Are uncorrelated with the error term. So essentially we have the correlation between xi and e is 0. That's what we're assuming. And this is kind of the biggest problem because, as we've talked about in some of the previous videos, there are some very important variables that are very hard to measure or unobservable. Like, for example, in a wage equation, you might want to include something like work ethic. Well, if you have an omitted variable, that's going to bias some of your other estimates, and so this is kind of particularly for causal econometrics, the tricky one. But like I said, I'm gonna have an entire video on this in the next, and I'm gonna stop here since it's getting a little long. But here are the 5 assumptions: normality, no autocorrelation, no heteroskedasticity, no perfect multicollinearity, and no endogeneity. In the next video, I'll talk a little bit more about some of these violations of the assumptions, and then we'll talk in kind of quite a lot more detail in a separate video on endogeneity and how it can come from these 2 sources. So I'm going to end this video here. Thanks for watching, and I will see you in the next video.